In section 2.2, I promised you some additional double displacement reactions. And what kind of person would I be if I didn't keep my promises? Acid-base reactions are going to be the first of these. But before we talk about the reaction itself, we need to have some idea what it means to be an acid or a base, and to know how to differentiate between strong and weak acids and bases. There have been multiple acid-base definitions that have been developed over the years. In Gen Chem 1, we tend to focus on Arrhenius acids and bases, in part because of the very limiting definition of a base. In this case, limiting is going to equate to a touch easier, so we're going to go with it. Svante Arrhenius was a Swedish physicist and chemist who's given credit for being one of the founders of physical chemistry. As much as you can be a founder of something that already existed and you just named anyway. He worked in the climate science field, and yes, even back before his death in 1927, we knew that CO2 was going to be a complete environmental nuisance. Sometime around 1884, he worked with electrolytes, and his acid-base definition stemmed from that work. Fun fact, he definitely looks like he could have sold you oatmeal in the early 90s. You're too young to be familiar with this particular ad campaign, but basically, small children across the nation were bullied into eating their oatmeal by this guy, and they're still traumatized by it. Arrhenius defined an acid as a species that is able to donate a proton when it's added to water. This proton is a hydrogen atom that's bonded to something more electronegative than it is. So really, anything other than carbon. I use A as a placeholder here. We'll elaborate on the chemical formulas for acids in a bit. A is a standard generic anion here though. When an acid interacts with a nearby water molecule, the hydrogen, or that proton on the acid, is attracted to the water molecule, so much so that it tells its counter ion, the A here, to peace out, and it goes and hangs out with that water molecule. The addition of the proton creates the polyatomic cation, the hydronium ion, which changes the pH of solutions. A negatively charged anion is also formed in the process. We will simplify this hydronium ion here to just a proton when we balance our equations in Gen Chem 1, but know that it reappears when we get to Gen Chem 2 because this is actually what happens in solution. Hydrogen can't exist by itself. It's going to form a hydronium ion each and every time. Know that we don't discuss pH until CH117 either. Most of you knew the term, so I used it. A little bit more on formulas for acids. Since an acid is going to donate a proton to water, its chemical formula is going to have at least one hydrogen present in it. But you have to be super careful because not all formulas that have hydrogen are going to be able to act as an acid in the first place. And not all hydrogens in something that is an acid are going to be acidic. There are two quick ways that we'll be able to recognize species that will act as an Arrhenius acid for our purposes here in Gen Chem 1. Either the proton or protons that will be donated to water are listed first in the chemical formula, or we will have an organic acid, which is a group denoted by this COOH. This group is called a carboxylic acid group, and if a molecule contains this group, it is referred to as a carboxylic acid. You'll have a ball with these when you get to organic. For now, you'll just have to recognize that this collection and this specific arrangement of these atoms leads to protons being donated when placed in solution. You'll also need to say something about how many protons might be donated. If there's a single acidic proton, which are underlined in blue, then you have a monoprotic acid. The prefix here should look familiar from our nomenclature. If there are two acidic protons in a chemical formula, then your acid is said to be diprotic. And if there are three acidic hydrogen atoms in your formula, your acid is said to be triprotic. Know that this conversation is more complicated than it could be, so we can't really use the phrase a diprotic acid will donate two protons to solution. We need to say that a diprotic acid can donate two protons to solution. We will work more closely with acids in Gen Chem 2, but for now, focus on just the wording. It might become a bit more clear when we talk about strong and weak acids in a second. I get asked 11 billion times a semester why we write out COOH instead of just condensing it. And that answer is that we don't really have to. CO2H also represents a carboxylic acid. But the expended COOH version is meant to better illustrate the connectivity of the group. But I don't care about that, you might say. Well, you really should, because that connectivity gives rise to the group's acidic nature and pretty much only that connectivity. Let's look at the line structure for butyric acid, our monoprotic example. Do not worry about reading the entire structure right now. I only share the image for the acid group, which I have highlighted here. The two oxygen atoms that are bonded to that carbon that magically appeared pull the electron density from that OH bond. This makes it relatively easy for that hydrogen to act as a proton and go find a water molecule floating around in solution. But only if these atoms are bonded in this order. A COH group can't perform this duty. Neither can an OH group. You have to have these four atoms bonded in this order so that this proton here can dissociate. There are 7 implied hydrogen atoms associated with this line structure as well, and none of those are acidic. This proton, and only this proton, has the potential to form hydronium ions we saw earlier. Only the 2 hydrogen atoms associated with the COOH groups are acidic in the propane 1,3-dioic acid. Though its structure appears more complicated, we can use the same reasoning to identify the acidic protons in citric acid as well. Some acids, when placed in water, lose a proton for every molecule of that acid. Let's say we have our trusty beaker of water and we have a sample of some acid. When these particular molecules are added to the water, they dissociate completely. But maybe I have a second beaker and a different sample of a different acid. When that sample is added to water, only part of it dissociates. And yes, these animations are reused electrolyte animations because acids, and bases for that matter, are electrolytes. An acid is considered a strong acid if it dissociates completely because that acid is also considered a strong electrolyte. An acid is considered a weak acid if it only partially dissociates because that acid is also considered a weak electrolyte. We will not see acids that are non-electrolytes because the two definitions can't work together. So how do you know if an acid is weak or strong? Well, you memorize these 7 strong acids. Yes, 7, not 6. HClO3 has an uncharacteristic high dissociation constant compared to other weak acids, and it is safer to consider it strong than something that dissociates incompletely. There are only 7, so this will not be one of the more robust memorizing tasks of your academic career, but it is a task for you, so get after it. There isn't a list of weak acids for you to learn, but if the acid is anything other than these 7, it will be considered weak. So learn the 7 strong acids and you'll know all of both groups. Arrhenius defined a base as a species that is able to donate a hydroxide ion when it is added to water. In order to donate a hydroxide ion, your base will have to, in fact, start with one. The generic plus sign here represents any cation, as these bases will be ionic compounds. When added to solution, the ions that make up the ionic compound will dissociate in the form of hydration shells, just like we saw in section 2.2. Much like acids can be divided into strong and weak electrolytes, bases are going to follow suit. There are 8 bases that will be considered strong. These are the hydroxide salts of the group 1 cations and the larger 3 group 2 cations. The group 1 salt should make sense to you here, as group 1 cations are always rurals and always soluble. The group 2 cations might be more confusing as strong electrolytes since they're listed as partially soluble in the solubility rules. While it's true that not all formula units for these salts will dissolve because the solubility really is lowish, which you can confirm by putting some of these in solution, you'll get a cloudy solution. What formula units do dissolve do so 100% completely. And they release 2 hydroxide ions per unit, which causes dramatic changes to the pH of solutions. This is in contrast to the smaller group 2 hydroxides, which are both insoluble and considered weak electrolytes. Some oxides, or O2- compounds, are also considered strong bases since the oxide released immediately forms hydroxide ions. But we're going to stick with these salts that directly donate their hydroxides to water. Anything else in the base category is going to be considered weak. That includes our other hydroxide salts that aren't these 8 strong ones. These are largely included on quizzes to trip students up. Their dissociation equations will look like any other salt dissociation, so just know that they're weak electrolytes. You'll also commonly see nitrogen-containing compounds acting as the base. The mechanism for the donation of hydroxide ions to water is fundamentally different and better described with a different acid-base definition. So we save them for Gen Chem 2. But since their addition to water does result in hydroxide ion solution, they are bases, even in the Arrhenius case. Super bonus fun fact, water can act as both a weak acid and a weak base. We're talking super weak. It's not really great at either one. But when water dissociates, both a proton and a hydroxide ion are formed and donated to solution. The proton makes the solution acidic in the same way that the hydroxide ion makes the solution basic, so the solution remains neutral. Here, neutral refers to both pH and charge neutral. The chemist would refer to water as an amphoteric substance because that term describes the ability to act as both an acid and a base.